Okay, so this is the last screencast from chapter 8, and it's a recording made after the lecture as a narration, as the sound recordings all failed on the 24th of November 2009. Anyway, where were we? We had just proved that the continuous image of a sequentially compact set is always sequentially compact, and I'd given you lots of warnings about how you could get the proof structure of that wrong if you were not careful. And then we had moved on after proving that and looked at the fact that continuous images of closed sets didn't have to be closed, continuous images of open sets didn't have to be open, and continuous images of bounded sets didn't have to be bounded, but somehow if you combine closed and bounded, then you get this additional information. And the continuous image of a set which is both closed and bounded is still closed and bounded, because that combination gives you this very powerful condition of being sequentially compact. Now, the particular case where the function is taking values in the real line is particularly important, and we start by proving a lemma in order to help us prove this boundedness theorem for sequentially compact sets. So the first thing we're going to prove is that if you've got a non-empty sequentially compact subset of R, then it has both a maximum element and a minimum element in it. Now, of course, we know it's going to be bounded because it's sequentially compact, and we said it's non-empty, so there'll be a least upper bound in R and a greatest lower bound in R, but you don't necessarily know that the least upper bound and the greatest lower bound are actually in the set, and that's decisive. If the least upper bound is in the set, then it will be a maximum element in the set, and if the greatest lower bound is in the set, then it will be the minimum. So here is the little note to remind you what happens if you've got a non-empty and bounded set. Then you do know that A has got a least upper bound, the supremum of A, and it's got a greatest lower bound, which is the infimum of A. But they might not actually be in A, and of course neither do the points in between them have to be in A. A doesn't have to be an interval. But we do have some information available. And the nice thing in this result is we know that A is closed, and that's going to help us. Now, if the supremum of A is in A, then it'll be the maximum element of A. And if the infimum of A is in A, it'll be the minimum element of A. And so that's what the main point of this proof is. So now we can actually start the proper proof of the lemma. So let E be a non-empty sequentially compact subset of R. then we know by the Heine-Borel theorem E is closed and bounded. Now, that means that we know, since E is non-empty and it's bounded, that it's going to have a least upper bound, supreme of E, a real number, and a greatest lower bound, inf E, which is also a real number. And now all we need to do is show that those two numbers are both in E. Now we'll do this for sup E because the proof for infimum is pretty much the same. So we'll show that supreme of E is an element of E because the proof for inf is similar. Now, actually, I didn't write down the fact that E was closed and bounded, so let me just go back and add that in. I said it, but I forgot to write it down. It's closed and bounded by the Heine-Borel theorem. Of course, that's what we're using here. Okay, now I'll put that back in. Let's get back down and carry on. And we're showing that the supremum is in because the proof for the infimum is similar. So let's set little s to be the supremum of E. Now, since s is the least upper bound of E, then anything slightly but strictly less than s is not going to be an upper bound for E, because little s is the least one. So if we say subtract off 1 over n, where n is a natural number, probably a very big natural number, we'll get something that isn't an upper bound anymore. So we let m be a natural number, and it's probably going to be a big natural number. Then s minus 1 over n is going to be a little bit less than s, but strictly less than s. It's not an upper bound for E anymore because s was the least upper bound. So that means there's a point of E which isn't less than or equal to s minus 1 over n. In other words, there's a point of E which is strictly greater than s minus 1 over n. Since there's one of these for each n, we'll pick out a point xn in E so that s minus 1 over n is less than xn. Or in other words, xn is greater than s minus 1 over n. Of course, xn is still less than or equal to s because s is an upper bound for E. So we actually have xn sandwiched between s minus 1 over n and s. So we've got s minus 1 over n is less than or equal to xn is less than or equal to s. And now you can either see directly, or you could even quote the sandwich theorem if you want, since xn is sandwiched between two sequences converging to s. But anyway, you can see that the distance from xn to s is less than or equal to 1 over n. So certainly xn tends to s as n tends to infinity. And of course xn is a sequence in E, which is converging to something. But E is a closed set. So that's going to get us the result we want. So we've got this sequence xn in E, it's converging to little s, the least upper bound, by, if you like, the sandwich theorem. Then, since E is closed, and xn is a sequence in E, which is converging to something, the limit, which is little s, has to be in E too, by the sequence criterion for closedness. Remember, if you've got a closed set, and you've got a sequence in the set which converges to something, then the limit of the sequence must be in the closed set as well. And that gives us what we want about soup, and the infimum proof is exactly the same. Let me remind you again that E doesn't actually have to be an interval. So it's not the case that everything between the least upper bound and the greatest lower bound is in the set. So not everything between the minimum element and the maximum element needs to be in the set. For example, here's an example of a closed set, which we've met before in the module. Here's an example showing that E doesn't have to be an interval. It could be this closed set, which is just got 0 in it, and then another sequence of points converging to 0, like 1, a half, a third, a quarter. And that's nothing like an interval, because it's only got, is really made up of a sequence of points converging to 0, and throwing 0 in as well. And it's closed and bounded. We can now prove the boundedness theorem for sequentially compact subsets of R to the D. This generalizes the boundedness theorem that you had last year for functions that are continuous on a closed and bounded interval in the real line. And of course, you can actually use this result to prove that one, as we'll see in a minute. But this is the more general one, valid for all continuous real-valued functions defined on non-empty sequentially compact subsets of R to the D. So the idea is if you've got such a function, then it will achieve some maximum value amongst all the values it takes, and it'll achieve some minimum value amongst all the values it takes. That means there's going to be a pair of points in D, called them P and Q, where f of P is the smallest value taken by the function on D, and f of Q is the biggest value taken by f on D. Now the proof is quite quick, given what we now know about continuous images of sequentially compact sets, and what we know about sequentially compact subsets of the real line. Non-empty ones have got a maximum and a minimum element. So all we do is we apply what we already know. So we take such a function f and d, and a domain D, now, since f is continuous and D is sequentially compact, we know that the image, the continuous image of a sequentially compact set is sequentially compact. This, of course, is a subset of R because the function f is taking values in R. So f of D is a sequentially compact subset of the real line. Now we assume that D was non-empty, so that will give us that f of D is a non-empty sequentially compact subset of the real line. Now we can apply that lemma. We know quite a lot about non-empty sequentially compact subsets of the real line. So by our lemma, we know that the image, f of D, has got a maximum element, which we'll call little b, and a minimum element, which we'll call little a. Now, A and B are in the image, f of D. That means that they are values taken by the function f. So there is some point Q in D, so that f of Q is little b. And similarly, there's a point P in D, so that f of P is equal to little a. And of course, these were carefully chosen to be the maximum and the minimum values taken by the functions, so the whole image, f of D, is contained in the closed interval from little a to little b. In other words, between little a and little b inclusive. And from that you get that little p and the points P and Q have got the properties we want. For all points x in D, we've got f of P is less than equal to f of x is less than equal to f of Q. And that's exactly what we wanted, so we finished. Now, as I said, this is a generalization of last year's result for continuous functions on closed and bounded intervals, the first year version of the boundedness theorem. But you can deduce that version from this one because if you do take a closed and bounded interval in the real line, it'll give you a sequentially compact set, and then we can apply this theorem. So let's have a look at that. If you take real numbers a and b with a less than or equal to b, then the closed interval ab is a closed and bounded set, and of course it's non-empty here, so it's sequentially compact, and we can apply our theorem, and you get the usual version of the boundedness theorem from last year, that there are a pair of points, well, that you achieve a maximum value and a minimum value. And I can give you a little sketch of that to remind you what this was saying last year. Yeah, so here you are. This is the last year's version of the boundedness theorem. That if you've got a continuous function defined on a closed and a continuous real-valued function defined on a closed and bounded interval, then it takes a maximum value and a minimum value amongst all the values it takes on the closed and bounded interval. So here's a sketch that helps you with this one. You've got your continuous function from this closed and bounded interval AB taking values in the real line, and because of this result, we'll find a place where it takes the biggest possible value amongst all the values taken on the interval. Now, we don't know anything about being able to differentiate this function, and we also don't know whether the points where you get the maximum and minimum value are the end points or in the middle. But typically you might expect something like this. Here's an example. In this particular case, the extreme values were taken somewhere strictly inside the interval, but it can happen at the end points, in which case there's no reason to expect it to be sort of flat like this. Anyway, so you know that there's going to be a pair of points, P and Q, in your closed and bounded interval, where f of P is the minimum value amongst all the values taken, and f of Q is the maximum value amongst all values taken. In other words, f of P is less than equal to f of x is less than equal to f of Q for all points x in your closed interval AB. Of course, you are assuming that this is a continuous real-valued function defined on your closed and bounded interval AB. Now, in this particular case, because you were working on an interval, you actually know that you get all the values in between as well, using the intermediate value theorem. Intermediate value theorem says you can't jump over any values, you can't miss any values out between two of the values you take if you're a continuous function defined on an interval. So not only is every value taken, not only are all the f of x's between f of p and f of q, but also you manage to achieve every value between f of p and f of q. And so if you actually want to know what the continuous image of this interval AB is, it's exactly equal to the closed interval between f of p and f of q. The closed interval consisting of all values between the minimum value and the maximum value, inclusive of course. And that brings us to the end of chapter 8.